Hello everyone, my name is Tingyu Cheng. I'm a fourth year PhD student at Zhang. Today I'm excited to introduce our project SwellSense, which seeks to establish 2.5D interaction with micro-capsule paper. Before I dive into the specifics of this project, I would like to thank all my collaborators, especially my advisors, Gregory and HyunJoo. Today we would like to talk about textures, which covers the surfaces of almost all the objects. No matter it is flat, curved, or in a more complicated 3D geometry, things are always patterned or textured. Even textures are to some extent pretty ignorable in our everyday life, but they indeed serve very crucial function. For instance, they can assist the human perception by allowing us to feel and differentiate between different objects. Additionally, textures can provide unique physical affordances, such as a handrail with a rubber handle that provides increased friction, making it better suited for tasks that require greater torque. More explicit patterns can even convey information and help individuals better understand and explore their environments. So we propose SwellSense, which aims to create 2.5D interaction with micro-capsule paper. Specifically, SwellSense aims to generate a diverse spectrum of swelling patterns and sensing modalities, while also prioritizing a low-cost and highly accessible fabrication approach. SwellSense is primarily built on the commercially available SwellTouch paper, also known as micro-capsule paper. This paper is heat-sensitive, consisting of a heat-triggered micro-capsule layer on top of the paper backing. Upon heating, the thermoplastic shells of microcapsules soften and the volume change filler begins to expand until the heat is released and the shell solidifies. In SwellSense, we print stretchable conductive inks directly onto the swell paper. These conductive inks serve the dual purpose of heating the microcapsule paper to form patterns and also supporting sensing capabilities along the surface. And the detailed fabrication approach includes three main steps. First, one needs to prepare the screen printing stencils, and then screen print and dry the stretchable conductive ink, and finally triggering the swell and assembly device. In order to trigger SwellSense, there are two primary methods. The first involves directly probing two ends of a pattern for uniform single-line heating. Alternatively, one can alternate the trace width within a single line for selective swell triggering, which can also be achieved by combining with a higher resistance carbon ink. We have explored how SwellSense can support a wide range of tactile or texture patterns. We showcase the four groups of patterns ranging from the most basic line geometries to more complicated ones, such as numbers, English letters, or even drawings. We also specifically explored how we can tune the line density to indicate different tactile information, such as direction. Finally, we demonstrated how to create repetitive surface patterns by leaving non-swell areas that are not covered by the conductive ink, enabling us to create various surface patterns. In addition to exploring different types of patterns, we have also studied how to use SwellSense to enable various sensing capabilities for different purposes. Capacitive sensing is the most common mechanism used, for example, by creating a button pattern that detects when users touch the swelled area. We can also extend this to other shapes like a slider or rotator. While most capacitive sensing scenarios involve direct contact with the electrodes, we have also experimented with adding a dielectric layer on top of the silver trace, such as Scotch tape or dielectric ink, to form an additional capacitor between the trace and the user's skin. Comparing to directly touched electrodes where the signal is more dominant by the capacitance from the human to ground, by adding this simple dielectric layer, the capacitance change between human skin to silver trace on the paper will play a bigger role, and allow us to achieve a single-pin multi-touch controller by enabling users to touch different density areas as individual inputs. Additionally, the dielectric layer can also be used to capture clear pressure stage differences when users press the pattern, reducing false triggers. We also investigated contact-based resistive sensing, using a folded sheet to form a two-layer mechanical switch that only closes the circuit when the top layer touches the bottom terminal layer. To enhance design customization and user support, we created a design editor. The backend is implemented with Grasshopper and Rhino in C#, and the front-end interface is built with Human UI. Users can generate designs by following these steps. They can first import a drawing file, and then select the design type and adjust the design parameters. Our design editor also allows them to view simulation results, and then finally they can adapt the recommended heating conditions and export design files for vinyl cutting. The heating parameters from our design editor are derived from our theoretical model for SwellSense. For the SwellSense system, we have our input power as P equals to V squared over R, where the generated heat is then mainly dissipated into the air and the paper substrates. When the heat dissipates into the environment, it follows Newton's law of cooling. The heat dissipation rate, dQ over dt, is proportional to the differences of the temperature between two adjacent materials. We followed the guiding theorem and by the end provide our final equation that for instant temperature as well as the function for saturation temperature for the system. We further carried out a design workshop with 11 participants with the goal of verifying the usability of our proposed method, including our design editor and fabrication techniques. And also we would like to explore the open design space. For our first goal, we asked the participants to heat up two identical 3 cm by 3 cm by 1 mm square patterns. One is given the heating parameters generated from our design editor, while one is not. When users have no clue of what power to provide for a pattern, they sometimes can use very low voltage and have to keep adjusting the voltage to trigger the swelling. Also, as you can see, 6 participants use a too high voltage, causing their designs to burn. We then continued the workshop with a design and a prototyping session. Here are the results. One is a paper horn containing functionalities like music tone adjustments by the capacitive touch pads, and sound volume adjustment by a resistive track on the side of the paper and a ring on the user's finger. The other one is quite interesting, which is a birthday card supports an interaction that allows people to touch the sensing area on the left side of the birthday card to start the swelling of the heart pattern on the right side of the card in real time. Besides these two applications, we have also further extended the use cases for SwellSense with the 6 following examples.
A, B, C, D, E, peach, strawberry. Peach's price in March 2022 is $1 per pound. Strawberry's price in February 2022 is $1.5 per pound.
Well, SwellSense is a simple and highly customizable fabrication approach to create 2.5D sensible surface textures. We still observe certain limitations. We chose our silver or carbon ink because of their great stretchability, but they are fairly viscous and only compatible with a screen printing technique, which could be time-consuming and ink wasting. So inkjet printing as a direct ink deposition method will help to improve the automation of the current fabrication routine. But the commonly used silver nanoparticle inks will not be compatible because of their extremely low stretchabilities of the inks. Instead, low temperature sinterin PSS or silver nanowires could be the future ink substitution. Also, the heating process is open loop without any fine-tuning capabilities for the swelling height. We believe that by involving a closed loop control, for example a temperature sensor, we can achieve finer control of the swelling height or a height gradient within the same sheet. When we see the swelling effects from SwellSense, what really occurs in my mind is how our nature grows molds or even bacteria. And for our case, SwellSense can grow different surface patterns out of the micro-capsule paper to augment our living environment. But this made us think that the molds will probably die and become part of the environment by the end, while SwellSense, which contains non-biodegradable microcapsules, will probably be piled around us as what we do to our microcontrollers. A future direction we would like to pursue is to develop a biodegradable version of SwellSense that can grow out of everyday surface, sense the environment, and interact with us, while by the end got buried in the soil and degraded without adding any environmental burdens. I think that's all for my today's presentation. Thanks for listening. Please check out our paper for more details.